Hi, my name is Annika, and I'm a second-year student studying electrical engineering at the University of Colorado Boulder. Today, we're going to learn about the electromagnetic spectrum. Before we introduce the electromagnetic spectrum and the different types of waves in it, let's do a quick recap on what waves are. A wave is a disturbance that carries energy from one place to another through a medium. The equation for the speed of a wave is defined as v is equal to lambda times f, where v is the speed of a wave, lambda is the wavelength, and f is the frequency. The speed of a wave depends on the material it is traveling through. The speed of an electromagnetic wave, including light, through a vacuum is always the same. This is represented by c, and the value of c is always going to be 300 million meters per second, or 670 million miles per hour. To get the speed of an electromagnetic wave, you need to divide c by the refractive index of the type of medium the wave is traveling through. The refractive indices are as shown in the table. Now let's jump into the E&M spectrum. The E&M spectrum is the entire range of E&M waves in order of increasing frequency and decreasing wavelength. This means that as you look from left to right on a diagram of the spectrum, the wavelengths get smaller and the frequencies get larger. The size of the wave and its frequency have an inverse relationship. Since speed will always be constant, if wavelength increases, then frequency decreases and vice versa. Also, all E&M waves are radiation, but the longer wavelengths do not carry enough energy in them to damage cells. Remember, the higher the frequency, the more energy in the wave. There are 6 waves in the electromagnetic spectrum. These waves are radio, infrared, visible light, ultraviolet, X-rays, and gamma rays. Radio waves have the longest wavelengths and lowest frequencies. Their wavelengths range from thousands of meters to 0.001 meters. The shortest radio waves are microwaves. Radio waves are used in radar, sending sound, TV pictures, cell phones, cooking, and satellite transmissions. Infrared waves, also known as heat, have shorter wavelengths from 0.001 meters to 700 nanometers and higher frequencies. Infrared is used to find people in the dark and in TV remotes. Visible light is what we can see in the E&M spectrum. Fun fact, the only type of electromagnetic radiation that we can see is visible light, and it makes up only a fraction of the electromagnetic spectrum. Wavelengths of visible light range from about 700 nanometers, which is also known as red light, to 400 nanometers, also violet light. Visible light frequencies are higher than the frequencies of infrared waves. Ultraviolet wavelengths range from about 400 nanometers to 10 nanometers. The frequency, and therefore the energy, is high enough with UV rays to penetrate living cells and cause some damage. We need UV rays to produce vitamin D in our bodies. Even though too much can lead to sunburn and skin cancer, UV rays are easily stopped by clothing. UV rays are also used for sterilization of materials because they kill bacteria in high enough concentrations. Although humans cannot see UV light, bees, butterflies, some small rodents, and some birds can. X-rays have wavelengths from 10 nanometers to 0.001 nanometers. They have enough energy to penetrate deep into tissues, but are stopped by dense materials such as bones. X-rays are used for examining solid structures such as looking for cracks in bones and bridges, and for cancer treatments. Gamma rays have the shortest wavelengths, less than 1/trillionth of a meter. Therefore, they have the highest frequencies and carry the most energy. These are the most damaging to tissues and can penetrate the deepest. They're really hard to stop. You would need a 3 to 4 foot thick concrete wall to stop them. Gamma rays are released in nuclear power plants, by nuclear bombs, and by naturally occurring elements on Earth. They're sometimes used in the treatment of cancer. To recap, what is the relationship between the size of a wave and frequency? And what about the relationship between a wave's energy and wavelength? Well, both of these have inverse relationships. What do you think engineers have done with their understanding of the electromagnetic spectrum? Well, engineers have designed many devices and instruments that use various types of waves found in the electromagnetic spectrum. Some examples are radios, X-rays, CT scanners, and sterilization techniques. These devices use electromagnetic waves in different ways, and since, as we've learned, some waves can be powerful and dangerous, engineers must understand every aspect of the electromagnetic spectrum to make the instruments and tools safe for people to use. Check out the lesson on the TeachEngineering website and then apply what you learned about the electromagnetic spectrum in our associated hands-on activity, developing and presenting design solutions. Waves go public!